So she is from MSAID, and she will talk about one model to predict them all. Accurate and fast zero-shot peptide spectrum prediction for any post-translational modification.
For the kind introduction. I'm very happy that I have the opportunity to speak in this session today, and I'm very excited to share our work on peptide fragmentation prediction, specifically introducing a model that extends its ability to predict peptide fragment intensities for any post-translational modification. Before we dive into the topic, a quick disclaimer that MSAID is a bioinformatics company. We develop and commercialize proteomics software, and the research shown today is also part of our development. So let's start by asking the question, why do we need peptide fragmentation prediction? When we identify peptides, proteomics search engines compare experimental spectrum to the theoretical spectrum of a candidate peptide. If we have a machine learning model that can predict fragment intensities on B and Y ions of a theoretical peptide, then we can compare experimental spectrum to the full MS2 spectra of the candidate peptide. On the picture, we see an example of experimental peptide on the experimental spectrum on the upper panel, and on the bottom, we see the prediction on B and Y ions for exactly the same peptide. If we measure the similarity between these two spectrum and integrate this score in peptide spectrum matching, we get more accurate peptide identifications. There's already several models existing that can predict peptide fragment intensities, and some of them are shown on the table. Let's compare PROSIT, AlphaPepDeep, MS2PIP, and MSAID's last year fragmentation model INFERYS 4 to each other. While most of these models can accurately predict fragment intensities for the peptides, when it comes to speed, INFERYS 4 is faster than all the other GPU-based fragmentation models. On the other hand, we have MS2PIP, that is a classic machine learning algorithm rather than a neural network, and it's deployed on the CPU and is faster than the other GPU-based models. But the most important question for this research is, can these models support predictions for any post-translational modification? In case of AlphaPepDeep and MS2PIP, the users have an option to take new training data and refine existing pre-trained model on the new PTMs. In case of PROSIT and INFERYS 4, we have a predefined set of PTMs for which we can predict fragment intensities. So the question is, how can we support prediction of fragment intensities on any post-translational modification? As already hinted in the last slide, data-driven approach is always a good way to start. If we have various training data to train our initial model, or if we have new training data points for the new PTM, so we can refine existing pre-trained model, this is always a very effective way to predict intensities. However, refinement can be time-consuming, and most importantly, we might not have new data points for the new PTMs. In this case, there's a workaround called peak shifting. Peak shifting is a rule-based approach that ignores modifications in the peptide, so we predict fragment intensities on unmodified peptide and then shift the MZ values on the PTM sides. While this is a fast solution, it's heuristic rather than real learning. So if we have a PTM that drastically affects the fragmentation pattern, then peak shifting can be ineffective. There is an alternative that is zero-shot generalization. This is an ability of the model to generalize and predict fragment intensities on the PTMs that it has never seen in the training data. Arguably, this is the most challenging task for the model because it has to reason on the modifications that has never been observed in the training data. So how can we achieve zero-shot generalization? For this, we need to teach chemical structures to the models. Traditionally, when we build fragmentation models, we treat modified amino acids as arbitrary tokens. So if we take an example of lysine acetylation and lysine propionylation, we would treat these modifications as two arbitrary integers, and the model would not know if there's any similarity between these two. However, on the pictures, we clearly see that lysine propionylation has extra CH2 group, while the rest of the molecule is exactly the same as lysine acetylation. And if we had a model that understands chemical structures, it would be easier for the model to reason on the lysine propionylation by knowing about lysine acetylation. So to achieve this and teach chemical structures to the models, we can use either graphs or molecular strings. Graphs are very interpretable and expressive because the concept itself is already very similar to how chemical structures are built. However, if we have a peptide with a lot of amino acids, we might get very large molecule in training or in inference, and it can be difficult to scale. On the other hand, we have molecular strings that are compact textual representation of chemical structures, and you might all be familiar with such format called SMILES. We use something more robust that are selfies. So let's talk about selfies. Self-referencing embedded strings are also representing chemical structures in textual form. However, they are more robust in a way that if we have a valid selfie string, that means that it always leads to a plausible chemical structure. So the bonding types and the valency rules are already correctly implied in the selfie string. On the picture, we see a short peptide with 4 amino acids, and we have different branches colored in different ways. And on the right-hand side, you see a corresponding selfie string with the corresponding colors, so you can see which substring corresponds to which branch in the molecule. And the question now is how we feed selfies to the model, because we know that we cannot learn directly from the strings. So we need to find a way to represent selfies as meaningful integer representation. For that, we use byte pair encoding. Byte pair encoding is an algorithm that tries to find 2 most common symbols in a sequence and merges that to create a new token. Let's take a simple example of a small selfie string that we see and try to tokenize it with byte pair encoding with the given vocabulary that has only 2 tokens, 0 and 1, corresponding to C and branch 1. In the first iteration, byte pair encoding would represent the selfie strings as several zeros and ones. But the next step is to try to find 2 most common symbols. In this case, 2 zeros are the most common symbols in the sequence, so byte pair encoding would identify that as a new token with token ID 2. So now we have a shorter sequence corresponding to the input selfie string. These iterations go on until we reach the number of vocabulary size that the maximum number of vocabulary size that we predefined before. And at the end, in this case, we end up with a vocabulary that has 6 tokens, and we can represent the whole selfie sequence as just 1 token. So you would already get an idea that byte pair encoding is a compression algorithm. And to show you this, we tried to take the whole human Swissport database and represented that as selfie strings, and then tokenize that using byte pair encoding on different vocabulary sizes. And as you see on the picture, the more tokens we have in the vocabulary, the less and less token IDs we need to represent the whole human Swissport database. And on the vertical lines, you see how many tokens we would need to represent a peptide with 40 amino acids. And at the end, you see that with a vocabulary size of 1024, we actually only need 21 tokens to represent a peptide with 40 amino acids, meaning that byte pair encoding can actually capture even bigger structures than amino acids. To go back to the point where we built our vocabulary, we see that we have 6 tokens in the vocabulary, and we have 5 different representations of the given input selfie string. So the question is, should we always go for the highly compressed tokenization, or can we show different variations of the same selfie string to the model? So it means that byte pair encoding actually allows us to do data augmentation, and we can even choose how granular our tokenization can be. So the model can have a tendency to always see smaller substructures, so to have more fine-grained tokenization, or to have more high compression tokenization, meaning that we always show smaller number of tokens to the model. You would already get an idea that if the model is familiar with smaller substructures, that means that it might be easier for the model to reason on the modifications that it has never seen before, because it's still familiar with some of the structures from the training data. However, this comes with the cost of prediction time. On the right-hand side, you see 2 models trained on different tokenization strategies, with fine-grained tokenization on the left and highly compressed tokenization on the right. For the first model, we need maximum sequence length of 288, while for the second model, we only need 34 tokens to represent our input. And as you see, the fine-grained tokenization model is 10 times slower than high compression tokenization model. So we clearly see that there's a trade-off between generalization and the speed. But to look at this in more details, let's look at the actual example of how these two models can generalize on PTMs that are unknown to it. In the first experiment, we took both high compression model as well as fine-grained tokenization model and showed exactly the same training dataset to both of them. However, we have hidden biotinylation and all the variants of biotin modification from the training. And you see the evaluation of these two models using spectral angle, and the closer the spectral angle to 1, the better the performance of the model. And as you see in this first experiment, both of the models have poor predictions on these new modifications because none of them has seen any modification that is similar to biotin or any of the variants of biotin. However, there's more interesting experiment coming where we train again these two models on the same training data, but now we include biotinylation and 2 variants of biotin modification in the training data. However, we still hide biotin phenol from it. In case of high compression algorithm, you see that the model still struggles to generalize on biotin phenol. However, this is not the case for fine-grained tokenization model because it's already familiar to some of the substructures of biotinylation or distillobiotin phenol, for example, and using that information, it can actually extrapolate on biotin phenol. But I already mentioned that we can get generalization, but with the cost of prediction time. And since speed is a priority to us, we decided to train INFERYS 5, a structure-based model with high compression tokenization. So we still retain the inference speed. However, this time we support many more PTMs than INFERYS 4. And you see the evaluation of the 2 models on different modifications on these violin plots. In the first 4 violin plots, you can see that we can still compare the accuracy to INFERYS 4 because INFERYS 4 already supported these PTMs. However, now we have a model that is still fast, that is based on the structure, so it learns from the molecular strings, but it supports many more PTMs than INFERYS 4. And I already mentioned that we retain the speed in INFERYS 5, even though we have harder task now to learn from the chemical structures. To see the results of how prediction time is for INFERYS 5 and to compare it to other fragmentation models, here we show PROSIT, alpha peptide, and INFERYS 4 compared to INFERYS 5. And you see that INFERYS 5 is significantly faster than PROSIT and even faster than alpha peptide. But what's more interesting is that INFERYS 4 is also faster than INFERYS 5 is also faster than INFERYS 4, even though the latest model has more complex tasks to learn from chemical motifs. So how is it possible that we get a model that is faster than other GPU-based fragmentation models? There are 2 answers to this question. The first is quantization. Quantization is a technique of mapping high-precision floating point numbers into lower precision representation. This happens after the model is already trained. So we first train a model, take the weights of the model, and optionally we can also take the intermediate outputs, so the activations of the model, and convert them from float 16 to float 32 to float 16 as the easiest example. And even though the idea is very simple, it still comes with the challenges that we have to adjust to which layers we apply this method because we can actually lose accuracy if we need to retain flow 32 for some of the activations or some of the weights, for example. The other technique that helped us to speed up the new model is knowledge distillation. Knowledge distillation is a technique that transfers the knowledge from a very accurate large teacher model to a smaller student model. This helps us to first train a very large model that reaches the accuracy that we want, but then to train a second model that has a smaller number of trainable parameters, so it's still easy to deploy for real-time applications, but we still don't lose accuracy. How is this possible? So student has actually 2 tasks. The first task is to in this case, predict fragment intensities as close as possible to experimental data, and this is defined as hard loss, but it also has a task to mimic the predictions of the teacher model. So we define that as a soft loss, and this is a comparison of teacher prediction versus student prediction. And to sum these two up, we get a distillation loss that is objective function to train our student network. And this helps us to retain accuracy and to not lose the speed. And on the picture, we see how these two techniques affect our model. And you see that distillation speeds up the model by 20%, and plus quantization speeds up with 50% more. So what did we achieve with this research? We have a new model that can directly learn from chemical structures using selfies. But this also means that we don't have to encode only peptides, but now we can encode any molecular structure using the new model. And even though we deal with the chemical motifs in the input, we are still faster than other fragmentation models, including INFERYS 4. And we also learned that fine-grained tokenization actually enables us to extrapolate on the PTMs that the model has never seen in the training. However, this approach still comes with a few challenges. The first is that users are not yet able to define new structures for us. So there needs to be an interface for the user to be able to define new structures, so we can support that in the model that can extrapolate on new PTMs. Also, now that we can encode any molecular type, the next reasonable step might be to also be able to decode fragment intensities for different types of molecules, so beyond B and Y ions. And as always, we need more and more diverse training data so we can support existing PTMs more comprehensively, but also broaden the number of PTMs that we support with the next models. And at the end, I want to thank my supervisor, Siegfried Gesulat, for supporting me throughout this project, and everyone at MSAID who contributed to this project. And if you're curious about more scientific content from us, do not miss our upcoming talks today and on Thursday, and also feel free to stop by at 2 of our posters today. Thank you so much for your attention.
Great talk, Lizzie. My question is, using the smiles or the selfies to encode the peptides with the modification, is this potentially a way to encode like small metabolites as well and predict metabolite fragments?
Yeah, that's actually a very good question. Selfies, or smiles and also selfies, can encode any molecular structure, including metabolites. And this is why it would be a very reasonable step if we could be able to decode fragment intensities for this kind of molecules as well, because then we would have really one model that predicts them all, and we can predict not only peptide fragment intensities, but also metabolites and other molecular types.
Thank you very much for your nice presentation. I only had a question about the QCing of the selfie representation for the peptides. So how do you QC this? So how you ensure that this is the true way for the representation of the peptides?
Yeah, so one of the advantages, as I mentioned, for selfies is that if we have a valid selfie molecule, then we know that the molecule, valid selfie string, then we know that the molecule that it leads to is also plausible. And in case of, if you mean the modifications, for example, that we support this time, we are aware of how the structures look like. So we first build the selfie strings that corresponds exactly to that molecular structure, and then we train the model using these PTMs. Okay. And if the user were able to define new structures for us, because this is a structure-based approach, then we would be able to support even more and more PTMs.
Yeah, because just there are sometimes small nuances in the accuracy for the smiles representation. So I just wanted to be sure that you QC that for the selfies as well. Thank you.
Let's thank our speaker once more.
Thank you.